Welcome to the Fair Value Pro series of instructional videos covering the topic of fair value as defined in the International Financial Reporting Standard IAS16 Property, Plant and Equipment. My name is David Edgerton from APV Valuers and Asset Management, and I will be presenting this series of presentations. Some countries have their own localised version of IAS16, but the key concepts and requirements are essentially the same. This presentation provides an overview of two key aspects: useful life and residual value. Greater detail about some of the other key concepts and the practical aspect of its implementation are included in a range of supporting presentations which can also be found on the Fair Value Pro website. IAS16, Property, Plant and Equipment, deals with non-current physical assets such as land, buildings, roads, water, sewage and marine infrastructure, parks and other recreational assets. Within the definitions, there are three key aspects which require some consideration. Depreciation is the systematic allocation of the depreciable amount over the useful life. This means that the process must be logical and based on some form of systematic approach. The residual value is defined in terms of the amount the entity would obtain from the disposal of the asset at the end of its useful life. The useful life is limited to the period in which the asset is expected to be available for use, or defined by number of production units. These definitions are extremely important, but unfortunately often misunderstood, especially with respect to assets which have their life continually extended beyond the original design life via renewal or cyclical maintenance. Critical to the definition is that you don't actually have to dispose of the asset. It is based on an estimate of what the remaining value would be when it reaches the point in time when the asset is no longer available for use. In practical terms, this would typically be either at the intervention point or a point where the asset would no longer be considered suitable for continued use and therefore would need to be withdrawn from available use. Certainly for assets that are continually renewed to maintain their condition above a defined minimum standard, the end of useful life is not a theoretical design life based on how long the asset might last if it wasn't maintained. It is important that due consideration be given to the actual asset management reality when trying to develop an appropriate valuation and depreciation methodology. The following diagram demonstrates the risks of not applying these concepts correctly based on the actual asset management reality. As the asset ages, it is consumed. Through cyclical maintenance, it is renewed or relifed. This restores the asset's service potential. This process is repeated in order to keep the asset delivering a service at the desired level. We can now see that a portion of the asset's value is not consumed, but is retained. This can be seen as being equivalent to the residual value. The balance being the gross current replacement cost, and the residual value is by definition the depreciable amount. When the asset reaches the point requiring intervention, it is considered no longer available for use, and therefore this signifies the end of the useful life. As a result, the period between these points is the useful life. Estimating the useful life based on a theoretical end of design life can create significant risks and errors as shown in these two commonly applied scenarios. Both result in significant misstatement of both fair value and depreciation expense. So what does this mean? Clearly, both useful life and residual value need to be considered in relation to each other. The residual value can only be assessed once you have identified the end of the useful life, and it must be based on an assessment of the inherent value remaining at that time. Any assumptions that are made which do not attempt to reflect the actual asset management reality pose a severe risk of materially misstating both the valuation and depreciation calculations. The following diagram provides a simplistic view of the concepts and usually is the way the concepts are taught at school and university. Firstly, the gross current replacement cost of the asset is determined. Consideration is then given to how long the asset will be of use to the entity and what the potential proceeds from disposal will be at that time. This defines both useful life and residual value. The difference between the gross current replacement cost and the residual value is by definition the depreciable amount, which is the portion that needs to be depreciated over the useful life. This needs to be done using a method that matches the pattern of consumption. For the purpose of this presentation, we have assumed the pattern is constant, so we would apply a straight line to the calculation. When the time comes to do evaluation and assessment is made of the level of remaining service potential, this then provides the depreciated current replacement cost, written down value, or fair value. Following the process, the asset may experience a number of renewal cycles, each with its own useful life. The residual value existing in the old asset, however, has not been disposed, but instead has been transferred from the old asset into the new asset. In layman's terms, the entity has obtained value from the old asset equal to the residual value, and this value has been invested in the new asset. To further reinforce the concepts, I want to use a simple analogy of the level of water remaining in a bottle. We can directly measure the remaining value based on the level of water, assuming of course that the water is not affected by other factors such as being unfit to drink or contaminated. We will consume the water during the day, just as an infrastructure asset's service potential is consumed, and will top the bottle up when it reaches a certain point. This is akin to undertaking some form of capital expenditure when the asset reaches a certain condition or level of service. The top table records the activities during the day and the impact of the level of water in the bottle. The chart below shows a visual representation of the remaining value and rate of consumption. We start the day with a full bottle of water and a pre-breakfast walk. During the walk, we consume 75% of the water. After breakfast, we top the bottle up prior to leaving for work. By morning tea time, we have consumed some more, and the bottle is now only 50% full. By lunchtime, we have now emptied the bottle completely. After lunch, we fill the bottle back up again, and over the course of the afternoon, completely empty it. After work, we top the bottle up again and go to the gym for some more exercise. By the time we get home for dinner, the bottle is now only 1/4 full. Many of the traditional approaches adopt simplistic assumptions which utilize easily accessible data. The data may be factual, such as opening and closing value and time between the measurements. But if the key assumptions do not reflect the asset management reality, including the pattern of consumption, the end result can lead to material misstatement. Typically, these include simplistic assumptions that the pattern of consumption is constant and the useful life is the time from original commissioning to now, plus the estimated remaining useful life. This might be convenient, quick and easy, but can lead to major errors. Using this approach, we would calculate the amount of water consumed, being the accumulated depreciation, at 1 p.m. as being equal to the time that has passed since the start of the day, 6 a.m. to now, which equals 7 hours, divided by the total time between measurements, 13 hours, by the gross, 100%, less the residual value at the end of the day, 25%. This equals 7/13 of 75%, which equals 40%. As a result, we would estimate the written down value as being 100% less 40%, which equals 60%. However, this is incorrect, as we know from measuring the level of water at 1 p.m. that it was completely empty and the accumulated depreciation at that time was 100%, not 40%. The resulting risk of error can be shown by comparing the actual measurements with the estimated measurements based on the simplistic assumptions. At 1 p.m, the traditional approach has estimated the amount consumed as being 40%, with the fair value being 60%. This of course is incorrect and has resulted in material misstatement of both the fair value and the associated depreciation expense. If we had based our estimate on the factors that directly determined the level of remaining service potential, i.e. the level of water, we would have valued the water as being nil, as it had all been completely consumed at that time. This highlights the need for the methodology to reflect the asset management reality and to utilise the factors that directly indicate the level of remaining service potential, rather than relying on simplistic assumptions used for convenience. In summary, there are a number of key lessons to be learnt. Useful life and residual value are linked through their definitions and therefore need to be considered in light of each other. It is also critical that when developing a valuation and depreciation methodology, it is essential that the methodology takes into account the asset management reality, rather than being based on theoretical simplistic assumptions. This includes ensuring that the fair value and associated depreciation calculations be based on factors that are relevant. They should provide direct evidence of the level of remaining service potential. Approaches that rely on simplistic assumptions that have no direct relationship or do not provide direct evidence more often than not result in materially misstated results. The classic example is trying to use age and age alone, because it's convenient and easy to calculate, to estimate the level of remaining service potential without even taking into account the key factors such as condition and assessment of holistic aspects such as functionality, capacity, utilisation, obsolescence, etc. Failure to take into account these types of factors would also be a direct breach of IAS16. Finally, you need to be prepared to challenge your existing paradigm regarding the concepts of residual value and useful life. In the case of assets openly bought and sold, it is the trade-in or resale value at the time of disposal. This, of course, is what we are all taught at university. However, for assets such as those held by the public sector, this is not the case. These types of assets tend to be constantly renewed or relifed through cyclical maintenance, and as a result, the useful life is constantly changing. As a result, the residual value can be thought of as the inherent value remaining in the asset at the component level at the time when the asset reaches a point when it is considered to be no longer available for use. Typically, this would either be at the planned point of intervention or when the asset reaches a condition where it would need to be closed or decommissioned. Approaches that base these concepts on an eventual scrap value at some theoretical total end of life fail to take into account the asset management reality and typically result in materially misstated results. I hope this brief overview of useful life and residual value has been useful. Fair Value Pro is the world's leading software specifically designed to enable entities to take control over the fair value process. It makes IFRS valuations simple. The Fair Value Pro website includes a range of other educational materials, including the free 160-page practical guide to fair value and depreciation. We also welcome questions and comments via the Fair Value forum on the Fair Value Pro website. You can also contact me directly on info@fairvaluepro.com if you have any questions of either Fair Value or Fair Value Pro.